Welcome back. This week for Module 13, we'll be taking a look at two more labs, Lab 20 and Lab 21, and both of these exercises are going to come straight out of the lab manual. So we will start with exercise 33, looking at plate tectonics, and that you can find on page 223 in the lab manual. So as a quick overview for those of us that are not familiar with plate tectonics are these giant continent-sized plates that are more or less moving across Earth's surface, or more or less they're moving on top of the asthenosphere, which we'll get into in a second. But really, as these plates move, they pull apart, they collide, they slide past one another. This is what is largely responsible for any tectonic activity, aka earthquakes, as well as volcanic activity. We've touched on some of this, but for a little bit more detail, we will dive into it, right? So these continent-sized plates, this is also the theory of continental drift. Perhaps you've heard of Pangea. This is when all of the land mass that existed on Earth's surface was all congregated, and over the last 200 million years or so, the continents have drifted apart. So you can see going from A to B to C to D, and this is where we are in present day. And so the point is that using continental drift, using this theory of these continental plates, we can see how these continents have slowly drifted apart as they've moved along the asthenosphere. So without going into too much detail, we're just going to look at the overview of Earth's interior. So there are four main layers, but really what we're going to be looking at is just going to be this top portion here. And so ultimately we have the ocean. As we're going into Earth, we have the crust. Then we get into the asthenosphere and the mantle, and everything in here, obviously except for the solid inner core, is going to be liquid or viscous, meaning that it is not solid and has the ability to flow. And so as heat is being transferred around these areas, that is what is powering the movement of these giant continental plates. So this is really what we're interested in, right? This is going to be this top portion right here. So not only the crust, which is the outermost shell. So when we get into the asthenosphere, this is all a part of the mantle, but this is already molten rock. So this is viscous rock that is flowing. And so there's convection of heat, and as that is coming up towards the surface and moving along, this is actually what is moving and pushing and pulling these various chunks of crust, right? These continental plates. And that is really what is driving how the crust is being moved along Earth's surface. It's also important to note that there are two different types of crusts, oceanic crust and continental crust. Oceanic, is going to be thinner, made of denser rock, and continental crust is going to be thicker, made of less dense rock. And so this is important to remember because when they are colliding, continental crust will always stay on top of oceanic crust because it is going to be more buoyant because it is less dense. So major tectonic plates, this is more or less the same map that you saw initially. This is the map that you're going to be seeing in your lab exercise, and so you can see the general movement of all of these massive continental plates that are being pushed around Earth's surface. There's also a video that I've posted into the module. There are two additional questions you may want to pay attention to. This will help you understand or realize whether or not you understood what the video is actually talking about. But this is a very interesting video that I also recommend you take a look at if you would like a little bit more information about how plate tectonics work. But so when we talk about plate tectonics, and there are three main types of boundaries. There are going to be boundaries where the plates are sliding past one another. We call this a transform boundary. Divergent plate boundaries means that the plates are sliding away from one another. And a convergent plate boundary is where plates are sliding towards one another. And so you can see these highlighted in different areas around the globe. But importantly, again, if we have two oceanic plates that are sliding towards each other, one of them is going to be forced under another. But in every situation where we have an oceanic crust and a continental crust, the oceanic crust is always going to be diving down. The divergent boundary, as I said, is where we have two different plates that are moving away from one another. This is, again, driven by that heat, by that upwelling is what we refer to it, of the asthenosphere. So this is the liquid magma that is coming up, rising towards Earth's surface. And as there's new material forming and hardening, this is what is starting the spread of, in this case, it is the oceanic floor. So the spreading of this ridge, the spreading of this oceanic floor is what is moving this plate, right? Because this is a plate boundary. So this plate will be moving to the left and this plate will be moving to the right. And that is because of this upwelling. And that is what creates this divergent plate boundary where the plates are moving away from one another. So that was the example in the ocean, but we also see this on land. And so this is the continental rift valley. This is actually found in Africa. And so we can see the same thing. We have this upwelling. This is starting in the asthenosphere where more material is being forced up. You can see there's clues that volcanoes might exist here as a lot of this magma is making its way out of Earth's center up towards the surface. And so this is also, in essence, creating more crust, forcing these different plates in opposite directions. So they are diverging from one another. The convergent boundary is going to be the opposite. So instead of the plates moving away from one another, they are moving towards each other. And so it's also good to know that these are a quote-unquote destructive boundaries, meaning that material is being returned back to the mantle. Mantle being, the asthenosphere is the top part of the mantle. So we can see that as these two plates are moving towards one another, this oceanic crust is being forced back under the continental crust and back down into the asthenosphere, back down into the mantle, where all of this material is going to start to melt. It's being deconstructed. This upwelling where this magma again is going to be rising towards the surface. It's closely associated with more volcanic activity along these types of borders. And so we can see this happening again over a continent where we have these volcanic mountain chains that can happen quite often, or this can also take place over an ocean. And this is often where we will get islands forming. So we get these island chains or these island arcs that exist when two different plates, two different oceanic plates are colliding. One is subducting, and then as this material melts, this will again move towards Earth's surface and create these volcanic island chains. So keep this in mind because you will need to identify this in the lab manual. So the three different converging boundaries that we can see are going to be oceanic to oceanic, oceanic to continental, as well as continental to continental. So we just talked about this forms an oceanic trench, and when the plate is subducting, this can create volcanoes and volcanic arcs as the magma rises to Earth's surface. This is, again, a great example, something you'll need to pay attention to for the lab manual, but these volcanic island arcs are what can be created, and we can see this as the oceanic crust goes under the other oceanic crust, creating this ridge of islands or this island arc because we can see this long trench, this trench right here. And as the plate is being subducted, so we can see shallow, intermediate, or deep, meaning that this is going to be lower into Earth's surface as these areas. So these yellow dots would in essence be right around here. The orange dots are going to be about here, and those red dots deep are going to be right around here if you're able to visualize how this works, right? The earthquake map. So we can see that the plates are deeper the farther under this oceanic plate. And so this is also what creates these island arcs or these island chains in the middle, quote unquote, of the oceans. And another one is, again, the continent versus continent when two plates collide, and if no subduction occurs, so in essence, They're just getting scrunched up, and if one plate is not going under another plate, that means that the earth material or that crust material is going to get crunched, and it has to go somewhere, so it's going to go up. And so using the Indian plate as it hits the Asian continent, and that is what has resulted in creating the Himalayan mountains. So Mount Everest, the tallest or highest mountain on Earth's surface, is one of these mountains. And so you can see the forces that exist, or the forces that are at play here, again, over millions and millions of years. But that is what is creating these really high mountains as these two tectonic plates are being, ran into one another. And the last boundary, and this is one that we are probably a little bit more familiar with here in California, is the transform boundary. So that's where two plates are sliding past one another. The San Andreas Fault is arguably the fault line that we are most familiar with here in California. You can actually see the evidence of the fault line just from aerial photography. But we can see how one plate, the North American plate, is sliding southward, while the Pacific plate is sliding northward. But we can see these different fault lines. We can see how these different fault lines are moving. Again, there's no subduction taking place here, as these plates are just sliding along one another. And so this is also something that can create a lot of earthquakes. And ultimately, the Pacific Ring, this is the most volcanic activity in the entire world is located around this Pacific Ring, and this is where all of these other tectonic plates are basically running into or interacting with the Pacific Plate. So 75% of all volcanoes are associated with the Ring of Fire. So you may be asking yourself why some of these random volcanoes exist in the middle of nowhere. Maybe we're familiar with this chain of islands right here. This would be Hawaii. So let's talk about that. We call these mantle plumes or hotspots, but a mantle plume is in essence just volcanic activity that happens in the middle of a plate. Scientists theorize that there are just some natural weak spots where the hot material will rise through the actual, in this case it's going to be the oceanic crust, and make its way towards Earth's surface. And so where we have this extra hot spot or these mantle plumes, these hot spots are going to create volcanoes and create volcanic activity. And so where we have these hot spots, you can see that crust is going to be forming on top of just the oceanic crust. As the plate is moving, paying attention to the plate motion, the plate is moving to the left. So at one point, this hot spot was here, created this little mountain or this volcano. The plate continued to move, created this volcano. Now the hot spot, which is stationary, the plate is moving over the hot spot, is creating this volcano. And so depending on how fast it's moving or how slow it's moving, it can create these various island chains, Hawaii being a great example of this. So the plate, right, the Pacific plate is moving northwest, and the hot spot, which is stationary, is creating this island chain over various millions of years. And so you can see this Hawaiian chain is much larger than really what we're familiar with. We think of Hawaii as these islands right here, but you can see the evidence of this hot spot, which has existed in this location, has created all of these island chains because the plate has been moving across this location. So keep in mind hotspots, the mantle plumes, the various tectonic activity, how these plates interact with one another, and most importantly, how these volcanoes are formed, and understanding how when a plate subducts under another, we can see the magma coming towards the top, and you should be able to identify where we have shallow, aka closer to Earth's surface, or deeper earthquakes happening. Again, you have to think about this on a three-dimensional plane. So hopefully this is interesting. I think plate tectonics are really fascinating. Again, they explain how the world literally looks the way that it does. Tectonic activity, earthquakes, volcanoes, And again, I think most interestingly, these hotspots, which create things like the Hawaiian Island chains. So there's more additional supplemental reading, again, in exercise 33 in the lab manual. Definitely take a look through that. Take a look at that video, additional video that I've posted. But I hope you find this interesting.